Assalamu alaikum dear students. Welcome to the lecture of the classical mechanics. In this we will discuss the solution for the problem number 7.32, which says that the particle moved in a spherical symmetric force field with potential energy given by U of r is equal to minus k over r. Calculate the Hamiltonian function in spherical coordinate and obtain the canonical equation of motion. Okay, so these let's go to solution for this problem. First, because consider particle of mass m which move in spherical symmetric force with potential energy given by u of r is equal to minus k of r. So because particle is moving in spherical symmetry, so we will have velocity vector in spherical coordinate which is equal to this. Okay, we already studied this in the previous classes. And then the mod of velocity will be equal to r dot square x one component square plus other component square and third component square. So modulus will be equal to this. Then Lagrangian, which is equal to t minus u, and you know that t is equal to 1 by 2 mv square, and we can find its square by taking the square on both sides. So it will be equal to m over 2 r dot square plus r square phi dot square sine square theta plus r square and theta dot square. Then potential energy is given u is equal to minus k of r, so u of u is equal to minus k over r. Just plugging these value of kinetic energy and potential energy in the given formula, so this will give us Lagrangian, which is equal to m over 2 l square phi dot square sine square theta plus l square theta dot square plus k of r. This equation is represented by 1. Okay, then the momentum, generalized momentum, we can find the generalized momentum from this Lagrangian, which pr is equal to partial l over partial r dot, p theta is equal to partial l over partial theta dot, and p phi is equal to partial l over partial phi dot. So just taking the derivative of this Lagrange first with respect to r dot to find pr generalized momentum, then we will take the derivative of this Lagrange with respect to theta dot for generalized momentum p theta. Then for derivatives for the p phi generalized momentum along phi direction, we will take the derivative of Lagrange with respect to phi dot. Okay, by plugging the value of this Lagrange one by one in this expression and taking its derivative, this will give us pr p theta p phi. Okay, so we can find the value of r dot from this, value of theta dot from this, and value of phi dot from this. Okay, then we will use this in the next step. You know that Hamiltonian is given by h is equal to h, which is equal to sum of p and pq and q dot minus l. This is the generalized formula for this. So if we expand this summation, so it will be equal to h is equal to pr r dot plus p theta theta dot plus p phi and phi dot minus l. So we can find the value of r dot theta dot and phi dot as in equation 2. So these are the value of r dot theta dot and phi dot. So just plug these values in this equation respectively, and this will give h will be equal to pr square over m and plus p theta square over mr square plus p phi square over mr square sine square theta minus Lagrangian. We have already found the value of Lagrangian. Just plugging those values, it will give us the total Hamiltonians. So further simplification of this, if we use this 2 on this whole term, this will become h is equal to 1 over 2m pr square plus p theta square over r square plus p phi square r square sine theta minus k over r. So we can just combining some terms and rearranging this. This is the Hamiltonian, and then the derivative of the momentum, we can take the derivative of the momentum. pr dot is equal to minus partial h over partial r, p theta dot is equal to minus partial h over partial theta, and p phi dot is equal to minus partial h over partial phi, just taking their derivative. So we can see that p phi dot is equal to 0, and it means p phi is equal to constant. Okay, means generalized momentum along phi direction is constant. And similarly pr can be found by plugging the value of this h in this equation and taking derivative with respect to r. This will, the number of variable on which h depend reduced to 4 r theta pr p theta, because we know that p phi is constant, because h does not depend upon p phi, and h p phi is constant. So h will be equal to 1 over 2m pr square plus p theta square r square plus this minus k over r. For the motion with constant energy, say that the value of any of the four variable in this equation is fixed when the other three are given. So energy will be equal to 1 over 2m plus this whole term, because the Hamiltonian will be, energy will be equal to this total Hamiltonian, and we can find the value of PR, which will be equal to this. Okay, so these are the requirement of the question. We will not go to the simulation part, because we cannot draw that graph at this point. So I think mathematical derivations at this to this point is enough.